Welcome back. Section 6-8, Indeterminate Forms and Lapita's rule. Recall the limit x approaching 0 of sine x over x. This limit is equal 1. We had proved this result using geometric arguments in one of our early sections. Now, but a pedestrian approach would have resulted in, limit x approaching 0 of the numerator, limit x approaching 0 of the denominator, that would have fetched me 0 over 0. So, limits which result in such a form, 0 over 0, or sometimes infinity over infinity, these are called indeterminate forms. Indeterminate. We don't know whether zeros cancel. They don't really. But you know that limit x approaching 0 of sine x over x is 1. Likewise, you don't know sometimes whether infinities over infinity can somehow be manipulated to get you a pure number or not. Either way, such forms, such limits are called indeterminate forms. When you have indeterminate forms, there is Lapita's rule. Lapita's rule says, suppose f and g are differentiable and derivative of g, that is g here, at x is not 0 on an open interval I. So derivative is non-zero on an entire open interval I that contains number a except possibly at a. I don't care what happens at g prime at a. Alright, whether it's 0 or not. But f and g are differentiable and g prime is non-zero. All of this happens on an open interval I that contains a. Suppose limit x approaching a of fx is 0 and limit x approaching a of gx is 0. Suppose both f and g the limit is 0, or limit x approaching a fx is plus or minus infinity and limit x approaching a of gx is plus or minus infinity. Okay, so both f and g, they both approach 0 or they both approach one of the infinities. In other words, we have an indeterminate form of type 0 over 0 or infinity over infinity for the quotient. Okay. If you have an indeterminate form of this kind, then limit x approaching a of fx over gx is limit x approaching a f prime x over g prime x. In other words, if you don't know how to find when the limit is indeterminate, you can actually take derivatives. Now, this is where you need to know that for sure g prime x is not 0. Otherwise, denominator wouldn't, is not allowed to be 0. So, denominator should not be 0 on an entire interval. So, derivative g prime is non-zero on an entire interval. So limit x approaching a fx over gx is limit x approaching a f prime x over g prime x. Alright, so Lapita's rule, assumptions are f and g are differentiable and derivative of g is non-zero on an entire open interval I that contains a except possibly at a. Now, the proof of Lapita's rule. Okay. So, if you are indeterminate of 0 over 0 or infinity over infinity type, then you may as well take derivative. So, you want to see the proof. Now, the proof of this theorem requires a few other theorems first. Okay. But recall, Rolle's theorem, we had proved this long ago. Okay, in one of our earlier sections. Rolle's theorem says, let f be a function that satisfies the following three hypotheses. If a function f is continuous on the closed interval a to b, f is differentiable on the open interval a to b, and value f at a is value f at b. Then there is a number c in open interval ab such that f prime c is 0. So if you have a continuous function on a closed interval which is differentiable on its open interval such and the values at the end match, then there is a number between a and b. So notice open interval ab such that derivative at c is 0. So you will need this to prove Cauchy's mean value theorem. So notice our goal is to prove Lapital's rule, but we need a few steps before. So Rolle's theorem we have seen already. Now Cauchy's mean value theorem. This is a new theorem we are seeing. Suppose that functions f and g are continuous on closed interval ab. So two functions continuous on closed interval ab, and both the functions differentiable on open AB. Moreover, derivative of g is non-zero on the interval AB, open interval AB. So for all x in open interval AB. Why do I say g prime not 0? Because that's going to be in the denominator. Then there is a number c in open interval AB such that f prime c over g prime c is fb minus fa over gb minus ga. Okay, so derivative, quotient of the derivatives is quotient of differentials, if you understand what I say. Okay, so let hx, so we want to prove the Cauchy's mean value theorem. Let hx be fx minus fa minus this quotient times gx minus ga. So notice x is a variable and that shows up here and here. In other words, the right hand side is actually a function, a non-constant function. Okay, so hx is fx minus fa minus this fraction times gx minus ga. Then let's see what happens to h. H is continuous on closed interval AB. Why is it continuous? Well, fx is continuous, gx is continuous. If I subtract a constant from a continuous function, well, that's difference of continuous functions. Difference of continuous functions multiplying by a constant, then a difference of continuous and continuous. So the entire combination is called linear combination of two continuous functions f and g. In other words, h is continuous. Moreover, h is differentiable on open interval AB. Why is it differentiable on open interval AB? Well, it is a linear combination of two differentiable functions f and g. Same argument. Now you must ask, what happens if the denominator is 0? Look here, if the denominator were 0, gb minus ga is 0, then there would be, by Rolle's theorem, there would be an element c in the open interval AB such that g prime is 0. Okay? If gb minus ga is 0, then gb equals ga. Okay, I'm replacing f by g. But Rolle's theorem would tell me there should be a number where g prime is 0, but g prime is not 0 throughout the open interval. So you know the denominator cannot be 0. All right. So that without out of the way, we know that h is continuous on closed AB. H is differentiable on open AB. Now let's figure out what happens to the endpoints. H at A. I'm plugging in x equals A. X equals A. Okay, so that should be x equals a. So better write it down. All right, so x equals a. fa minus fa is 0. Ga minus ga is 0. 0 times anything is 0. 0 minus 0, overall 0. So h at a is 0. Fantastic. What happens to H at B? I'm replacing X by B. X by B. All right. FB minus FA, this number times GB minus GA. All right. Now notice GB minus GA cancels GB minus GA. So what do I have? FB minus FA minus parenthesis FB minus FA. Well, FB minus FA minus itself. It's 0. In other words, H at A is 0, HB is 0. So H at A is equal H at B. H is continuous on closed AB, differentiable on open AB, and H matches at the end points. So that was Rolle's theorem hypothesis. So there should be a number in between where H prime is 0. So there is a number C in between A and B, that is open AB, such that H prime C is 0. Once you have that C such that H prime is 0, well, let's look at our H. So when I take derivative, that's a derivative. This is constant, so its derivative is 0. This is constant, multiplying all of this, so that's G prime at C. This is a constant, its derivative is 0. So all you have is, there is a number C such that F prime C minus 0 minus constant times G prime Z, all of this is 0. That's what H prime C equals 0 means. Now let's move things about. This is a negative, I move it there. F prime C, that's left hand side, equals, move all of this to the right hand side. Divide both sides by G prime. So you have F prime C over G prime C is precisely this fraction. So this is what we wanted to conclude in our Cauchy's mean value theorem. What is Cauchy's mean value theorem? If you have two functions which are continuous on closed interval AB, differentiable on open interval AB, and G prime not 0 on the entire open interval AB, then there is a number C in between A and B such that F prime C over G prime C is equal FB minus FA over GB minus G. All right. Now with this information, we can get going with the Lapita's rule. Let's come to Lapita's rule in our next video. So proof of Lapita's rule will continue in our next video.